In this lecture, we continue discussing paradigmatic relation discovery. Earlier, we introduced a method called expected overlap of words in context. In this method, we represent each context by a word vector that represents the probability of a word in the context. And we measure the similarity by using the dot product, which can be interpreted as the probability that two randomly picked words from the two contexts are identical. We also discussed the two problems of this method. The first is that it favors matching one frequent term very well over matching more distinct terms. It put too much emphasis on matching one term very well. The second is that it treats every word equally. Even a common word like the would contribute equally as a content word like eats. So now we are going to talk about how to solve these problems. More specifically, we're going to introduce some retrieval heuristics used in text retrieval. And these heuristics can effectively solve these problems, as these problems also occur in text retrieval when we match a query vector with a document vector. So to address the first problem, we can use a sublinear transformation of term frequency. That is, we don't have to use the raw frequency count of a term to represent the context. We can transform it to some form that wouldn't emphasize so much on the raw frequency. To address the second problem, we can put more weight on rare terms. That is, we can reward matching a rare word. And this heuristic is called IDF term weighting in text retrieval. IDF stands for inverse document frequency. So now we're going to talk about the two heuristics in more detail. First, let's talk about the TF transformation. That is to convert the raw count of a word in the document into some weight that reflects our belief about how important this word in the document. And so that will be denoted by TF of W and D. That's shown in the y-axis. Now, in general, there are many ways to map that. And let's first look at the simple way of mapping. And in this case, we're going to say, well, if any non-zero count will be mapped to 1, and the zero count will be mapped to 0. So with this mapping, all the frequencies will be mapped to only two values, 0 or 1. And the mapping function is shown here as a flat line here. Right? And now this is naive because it ignored the frequency of words. However, this actually has the advantage of emphasizing matching all the words in the context. Right? So it does not allow a frequent word to dominate the matching. Now, the approach that we have taken earlier in the expected overlap count approach is a linear transformation. We basically take y as the same as x. So we use the raw count as a representation. And that created the problem that we just talked about, namely, it emphasizes too much on just matching one frequent term. Matching one frequent term can contribute a lot. So we can have a lot of other interesting transformations in between the two extremes. And they generally form a sublinear transformation. Right? So for example, one possibility is to take a logarithm of the raw count. And this will give us a curve that looks like this, right, that you are seeing here. In this case, you can see the high frequency counts. The high counts are penalized a little bit. Right, so the curve is a sublinear curve, and it brings down the weight of really those really high counts. And this is what we want because it prevents that kind of terms from dominating the scoring function. Now, there is also another interesting transformation called the BM25 transformation, which has been shown to be very effective for retrieval. And in this transformation, we have a form that looks like this. Right? So it's k plus 1 multiplied by x divided by x plus k, where k is a parameter. X is the count, the raw count of a word. Now the transformation is very interesting in that it can actually kind of go from one extreme to the other extreme by varying k. And it also is interesting that it has an upper bound, k plus 1 in this case. So this puts a very strict constraint on high frequency terms because their weight would never exceed k plus 1. As we vary k, if we can simulate the two extremes. So when k is set to 0, we roughly have the 0, 1 vector. Whereas when we set k to a very large value, it will behave more like the linear transformation. So this transformation function is by far the most effective transformation function for text retrieval. And it also makes sense for our problem setup. So we just talked about how to solve the problem of overemphasizing a frequent term. Now let's look at the second problem, and that is how we can penalize popular terms. Matching the is not surprising because the occurs everywhere, but matching it would count a lot. So how can we address that problem? Now in this case, we can use the IDF weighting that's commonly used in retrieval. IDF stands for inverse document frequency. Now document frequency means the count of the total number of documents that contain a particular word. So here we show that the IDF measure is defined as a logarithm function of the number of documents that match a term, or document frequency. So k is the number of documents containing word, or document frequency. And m here is the total number of documents in the collection. The IDF function is giving a higher value for a lower k, meaning that it rewards a rare term. And the maximum value is log of m plus 1. That's when the word occurred just once in the context. So that's a very rare term, the rarest term in the whole collection. The lowest value you can see here is when k reaches its maximum, which would be m. So that would be a very low value, close to 0 in fact. So this of course measure is used in search, where we naturally have a collection. In our case, what would be our collection? Well, we can also use the context that we can collect for all the words as our collection. And that is to say, a word that's popular in the collection in general would also have a low IDF, because depending on the data set, we can construct the context vectors in different ways. But in the end, if a term is very frequent in the original data set, then it will still be frequent in the collected context documents. So how can we add these heuristics to improve our similarity function? Well, here's one way, and there are many other ways that are possible, but this is a reasonable way where we can adapt the BM25 retrieval model for paradigmatic relation mining. So here we define, in this case, we define the document vector as containing elements representing normalized BM25 values. So in this normalization function, we take sum over all the words, and we normalize the weight of each word by the sum of the weights of all the words. And this is to again ensure all the xi's will sum to 1 in this vector. So this would be very similar to what we had before, in that this vector is actually something similar to a word distribution. all the xi's would sum to 1. Now the weight of BM25 for each word is defined here. And if you compare this with our old definition, where we just have a normalized count of this one, right? So we only have this one and the document length, or the total count of words in that context document. And that's what we had before. But now with the BM25 transformation, we introduced something else. First, of course, this extra occurrence of this count is just to achieve the sublinear normalization. But we also see we introduced the parameter k here. And this parameter is generally a non-negative number, although 0 is also possible. Right, this controls the upper bound, and it kind of also controls to what extent it simulates the linear transformation. And so this is one parameter, but we also see there is another parameter here, b, and this will be within 0 and 1, and this is a parameter to control length normalization. And in this case, the normalization formula has the average document length here, and this is computed by taking the average of the lengths of all the documents in the collection. In this case, all the lengths of all the context documents that we are considering. Right? So this average document length will be a constant for any given collection. So it actually is only affecting the effect of the parameter b here, right? And because this is a constant. But I kept it here because it's a constant that's useful in retrieval, where it would give us a stabilized interpretation of parameter b. But for our purpose, this will be a constant, so it would only be affecting the length normalization together with parameter b. Now with this this definition, then we have a new way to define our document vectors, and we can compute the vector d2 in the same way. The difference is that the high frequency terms will now have a somewhat lower weight, and this would help us control the influence of these high frequency terms. Now the IDF can be added here in the scoring function. That means we'll introduce a weight for matching each term. So you may recall this sum indicates all the possible words that can be overlap between the two contexts. And the xi and the yi are probabilities of picking the word from both contexts. Therefore, it indicates how likely we'll see a match on this word. Now, IDF would give us the importance of matching this word. A common word will be worth less than a rare word, so we emphasize more on matching rare words now. So with this modification, then the new function will likely address those two problems. Now, interestingly, we can also use this approach to discover syntagmatic relations. In general, when we represent a term vector to represent a context with a term vector, we would likely see some terms have higher weights and other terms have lower weights. Depending on how we assign weights to these terms, we might be able to use these weights to discover the words that are strongly associated with the candidate word in the context. So let's take a look at the term vector in more detail here. And we have each xi defined as the normalized weight of BM25. Now this weight alone only reflects how frequent the word occurs in the context. But we can't just say any frequent term in the context will be correlated with the candidate word, because many common words like the will occur frequently in all the contexts. But if we apply IDF weighting, as you see here, we can then reweight these terms based on IDF. That means the words that are common, like the, will get penalized. So now the highest weighted terms will not be those common terms because they have lower IDFs. Instead, those terms would be the terms that are frequent in the context but not frequent in the collection. So those are clearly the words that tend to occur in the context of the candidate word. For example, cat. So for this reason, the highly weighted terms in this IDF weighted vector can also be assumed to be candidates for syntagmatic relations. Now, of course, this is only a byproduct of our approach for discovering paradigmatic relations. And in the next lecture, we're going to talk more about how to discover syntagmatic relations. But it clearly shows the relation between discovering the two relations. And indeed, they can be discovered in a joint manner by leveraging such associations. So to summarize, the main idea for discovering paradigmatic relations is to collect the context of a candidate word to form a pseudo-document. And this is typically represented as a bag of words. And then compute the similarity of the corresponding context documents of two candidate words. And then we can take the highly similar word pairs and treat them as having paradigmatic relations. These are the words that share similar context. And there are many different ways to implement this general idea. And we just talked about some of the approaches. And more specifically, we talked about using text retrieval models to help us design an effective similarity function to compute the paradigmatic relations. More specifically, we have used BM25 and IDF weighting to discover paradigmatic relation. And these approaches also represent the state of the art in text retrieval techniques. Finally, syntagmatic relations can also be discovered as a byproduct when we discover paradigmatic relations.